Okay, so welcome to our presentation session. This is we're very happy to have our new branch for NYU SIAM started, and we are looking forward to. We have a lot of events coming up this semester. Just starting off with this research presentation, and coming up in the next few weeks, we've got very lucky to have Ajit Gary doing a special relativity seminar, where he's going to be doing a bunch of colloquiums, where he's going to teach about. He's going to be teaching about special relativity and some of his work. There's going to be some potential coding and workshop activities. So please just, if you want to go, please register. And please let us, I don't know, just let us know if you'd be interested in any other events coming up for the rest of the semester. We are a new branch. So anything would be, any advice or feedback would be appreciated. And then we've also got the math of the cell, which is, we're having another master student coming in and doing a six session colloquium with us. And he's going to be talking about, obviously, a little bit of computational biology, which should be interesting to hear. We're hoping to have a few more workshops, hopefully in the fall, that will be more targeted towards, maybe we'll get some people from business field, medical field, but at this moment, we're just trying to get some people to sort of bridge the gap between research and also industry for undergraduates. So we're very excited to have you guys here. This is going to be a little more theoretical of a presentation. We just conducted research last summer on a topic in algebraic geometry and also related to knot theory. And I hope you guys enjoy the presentation. So I'm going to actually first show you, just for reference, we actually, me, Matt, and Farhan all wrote a paper last summer, which is called about what we call the presentation of the Roger-Yang Generalized Skein Algebra. And we're going to obviously spend some time doing 3 mini presentations to just let you know about what our paper was about. This paper has been accepted to be published in Algebraic and Geometric Topology. And if you would like the link or any other information, be happy to give you. And lastly, if you have any questions, I will be checking the chats. If you want to write any question about any terminology that we say that's confusing, or any, I don't know, any question or suggestion that you have, please let us know. So I think we're going to start off with the presentation. So I'm going to start first. So I'm going to be going over the basics of what we did, some basic knowledge and what our main theorem was. And then Matt is going to, well, our main theorem was we essentially, there's something called a skein algebra, which is a collection of curves that can be defined on, for example, let's just take a sphere with a few punctures in it. If you were to look at a set of different curves, essentially, I'm going to be a little hand wavy. It's sort of classes of curves, but on the surface. And you allow 3 different operations on them. We define addition and multiplication.
Ryan, you're not sharing your presentation
Oh,
yet.
yeah, no, I know. I didn't want to
Okay.
give much information yet, but we basically found, for this set of curves along with these 3 operations, we found what is called a presentation, which is another way of understanding the structure of this set. We described something that's isomorphic, that has the same structure as, where we found a bunch of curves that can be combined to create every other curve. If you just add them, multiply them together, which we're going to define what that means. There's weird ways. It's weird to think of multiplying curves or adding them, but you can do that to any objects. It's not just numbers. You can do it with functions. You can do it with other matrices, other objects. So we're going to define what our generators are, which are the curves that can create all of the possible curves, relations, which I sort of think of as these sort of properties or equalities between curves that have to hold in order for our isomorphism to be true. And then we proved it for a specific, it's an algebra for a specific surface, because it's on curves for a specific surface. So we showed for the n punctured plane, so a plane with n holes in it. And then Matt is going to describe how we're going to transition that to working for a sphere, which just requires a little bit of thinking about just the pull of the sphere, which doesn't necessarily get mapped to perfectly from the plane. So I'm going to go start with my presentation. I have some slides, and if anyone has any questions or anything, please feel free to put them in the chat. We'll answer it as soon as whenever we see them. Okay, so let me share. Okay, so first I'm going to talk about the generators of the Skein algebra. So I think a few things that I probably should define first. First of all, that we're working on, well, first of all, just keep this in mind, working on a sphere with n punctures in it. And we're going to be looking at the set of different curves on the sphere. And it's important to distinguish how we define different types of curves. So we define, for example, what we're going to be doing with these things called multi-curves, which are essentially, we define them as one-dimensional manifolds that are made up of loops and arcs. We'll define those in a moment. A one-dimensional manifold is really just, if you can think of it in a simplified way, it's a differentiable surface. It's a nice behaving surface in many ways. That's an easier way to look at it. And an arc, the two types of curves that compose this multi-curve are going to be arcs and loops. An arc is just going to be a curve that starts at one puncture and connects to another puncture. And a loop is going to be a curve that goes around the punctures and doesn't touch any of them. So this diagram in the center is very, very illustrative of what a multi-curve is, which is just a combination of loops and arcs. For this arc, which we see from this puncture to this puncture, is just a curve that connects that puncture to that puncture. It's non-trivial, it's a little difficult to see, but that's one. And then a loop is a curve that goes around the punctures and doesn't intersect any of them. So we're going to define a set, which we're just going to, for notation and just for make it to simplify our work a bit, as R sub n is what we define as the integer polynomial ring, which is a set, and basically the variables will be the vertices of the on the sphere, and then the coefficients in front of those would be the variables for the polynomial, and then the coefficients would be integers. So what we define as the classical Skein algebra, we also did a more generalized version in our paper, is the classical Skein algebra is an Rn algebra generated by the regular isotopy classes of multi-curves, along with addition, scalar multiplication, and multiplication. So we define addition and scalar multiplication formally, meaning that there's no way to get any more simple. We can take a curve plus a curve, similar to like if you're adding x cubed plus x to the fifth. Can't simplify that anymore. We're just going to leave that as that. And we're going to define multiplication as taking the union of two curves, combining them. So our main theorem was we found what the curves that are necessary to create this set are, and we found what the certain properties that must hold through some, we did some calculations and a lot of pattern recognition. And what I'm going to focus on is the generators, which are what we call the beta ij's, which are just in many ways, it's just simple lines that connect the punctures. And those are enough, all the ones that connect the punctures and just straight lines would be the ones that essentially can create every single curve in this Skein algebra. So the statement that I'm going to be showing, which I'm going to be talking about, is that as an Rn algebra, which is just a technical term, the Skein algebra is generated by beta ij classes, and that any curve can be written as a product of vertices times the beta ij's. So we'll see some just long product and sum of those two different things. So first of all, I'll define what a beta ij is, because that's the main generator for our curves. The beta ij is, if we take two numbers I and j, where we just say I is a smaller number than j and it's an integer from 1 to n, beta ij is simply the simplest curve that can connect the ith vertex to the jth vertex, sort of a straight line on the surface. So I think a picture is very valuable here, and I'll zoom in because I know it's probably a little difficult to see. But for example, the simplest curve that connects the first vertex with the fourth vertex would be what we call a beta 1,4. So if we define, let's just say we lay out n punctures, or put just a bunch of punctures in a cyclic order on a circle. We draw a circle C through it, and then we label them from 1 to n. The first vertex, the curve connecting the first vertex to the fourth vertex would be what we call beta 1,4. And all of the other ones would either be the diagonals of this polygon, or it would be the sides of the polygon. It would be the complete graph on those vertices. So the idea of our proof is we can take any curve on the sphere and apply, now again, I may have forgotten to mention this, which is probably very important. Along with the Skein algebra, there's four relations which have been developed, which their motivation's a little more theoretical. I'm not going to get into them, but they come along with the Skein algebra. For example, if we have an intersection, let's just say some curve on the sphere has an intersection not at a puncture, then we can take that curve. This is just a local picture. This shows like a local part, very closed in. But we can take that same curve and say that it's equal to the sum of the curve of first of all, curve that's not intersected, but you see like this way, if we were to resolve the intersection, and one that's like that, as you can see from the photo. Or if you have one at a puncture, you can resolve it as V inverse times curve slightly above the puncture, slightly below, or an open circle or a circle with one puncture can be represented by numbers -2 or 2. So the idea of our proof, which we showed that any curve can be broken down into a product of VI's and beta IJ's, was to say, first of all, take a circle D that properly contains C. And now if we have a curve, which we're going to call alpha, it could be named anything, but we're going to put it on, that's on the surface. We're going to be able to deform the curve so that we can bring it inside of the circle D. There's nothing obstructing us from doing this. There's a way to just continuously deform it, because there's no punctures that are outside of D, because they're all properly contained in C, which is inside of D. So we're going to also draw some rays on this, well, at the vertices, and we're going to have them so that they're emanating outwards from each vertex, so that they're all disjoint, as you can see from this picture. We're going to call them R1, R2, R3. We're going to define for each curve, we're going to define a number, which is, we call, well, this is the number of intersection points between the curve and the rays, but we don't count intersections at the vertices, just anywhere else. And we're going to basically choose a minimal representative of curves that are regular isotopic, which is just basically, for the simplest case, can be deformed and there's a few other properties that are formally defined for what that is. There's a formal definition, but just we're going to choose a representative with the smallest number of intersections that's regular isotopic to that curve. And now we take that curve and we're going to induct and show that it works for any possible number of intersections. So just do a basic induction proof. We're going to show that if our base case is going to be if the intersection number is 0, meaning that the curve doesn't intersect any of the rays, then we're going to simply be able to just bring it inside of the curve, because there will be nothing. If it doesn't intersect, you'd be able to push in the curves in between the rays. There would be you can't touch the punctures because they're not there. They're physically, but you'd be able to move in the curves inside of the circle and be able to deform it into one of those line segments that I was describing before. And if we're going to suppose for our inductive step that if a curve intersects the rays k times, that it can be deformed into one of the beta IJs and brought inside. And we're going to look at the one that intersects k plus 1 times. And if we have a curve that intersects k plus 1 times, we can reduce the number of intersections by using this puncture Skein relation. We just solve for the curve that's inside, and we can reduce the number of intersections. And then now we have a curve that intersects k times. And by our inductive hypothesis, we know that that can be deformed inside. So that means for all all integers from 0 to, well, all integers, all positive integers, including also in 0, can be for any intersection number that is from 0 to infinity, we can bring in the curve and deform them into the beta IJs. So that was our generators. Those are the fundamental set. Farhan is going to talk about the ideals, which are special properties that are needed in order for our equality, or isomorphism, not equality, but isomorphism to hold. Okay.
All right, thank you, Ryan. So let me share my screen. All right, so in this presentation, we will describe the generators of J, which is the ideal. So this part of the presentation, don't worry about it because Ryan already went over it. But I do want to reiterate one thing. I just want to refresh our memories of what the beta ij's are. So let's say you have n punctures and they're all plotted in a counterclockwise order. Let I be less than j, and they're both contained in this integer set from 1 to n. Beta ij is just an arc that connects the ith puncture to the jth puncture. So it's a line segment that connects from vi to vj. Okay. So J is the ideal generated by 3 relationships. So let's talk about the first one. So let's say you have a 4 punctured sphere. Okay. So I'm going to zoom in a little bit. Let's say we have 4 punctures. No, I don't think this is going to work out. Okay, that's fine. So yeah, we have 4 punctures in the sphere, and let's draw beta 1, 3, and beta 2, 4. If you guys draw those two curves, you should get something that looks like this, right? It makes like an X. So at the intersection point, we could apply the first skein relation, and by doing so, you'll get something like this plus that. So beta 1, 4 times 2, 3 plus beta 1, 2 times 3, 4. Okay. So let's say you're in an n puncture sphere and we take 4 punctures, VI, VJ, VK, and VL. And let's draw BI, BIK, and BJL. Once again, you're gonna get like 2 arcs that form an X. And yeah, so that's how you draw the product of BIK and BJL. When they intersect, you could apply the first schema relation on their intersection point, which will result to the right-hand side of this equation. This is what's called the Ptolemy relation. Is everyone following so far? Okay, wonderful. Let's talk about the second relation. So let's say we have 2 vertices, VI and V3. So let's draw this arc that starts at VI, goes over V2, and ends up at V3. It looks something like this, right? We call this gamma 1, 3 positive. Okay, so if we're in an n puncture sphere and we pick VI and VJ, and we draw an arc that starts at VI, goes over all the other vertices until it reaches VJ, that's what we call gamma ij positive. Now let's look at this figure right here. So gamma 3, 1 positive has another name. We call it gamma 1, 3 negative. Gamma 1, 3 negative is an arc that starts at V1, goes in a it goes in like a counterclockwise order and ends up at V3. Okay, so if we were to draw if we're in an n puncture sphere and we would like to draw gamma ij negative, it's an arc that starts at VI, goes in a counterclockwise order above all the other vertices and ends up at VJ. So let's take a look at this figure again. Let's take a look at gamma 1, 3 positive. So note this is on a sphere. So what we could do is we could take that arc and we could like drag it behind the sphere. And when we drag it all the way behind the sphere, we will get gamma 1, 3 negative. So when we do the same thing, apply the same idea with gamma ij positive and gamma ij negative, you should see that they are the same. This is what the gamma relationship is. Mhm. The gamma relation, I bet. Okay. Now let's talk about one last relation. So let's take a loop that surrounds all end punctures of the sphere. What we could do is we could take this loop, we could push it away from these punctures, and by pushing it away, we're dragging this loop behind the sphere. And by doing that, we should get a loop that does not contain any punctures. And by the, what's this relationship called? By the puncture framing relation, I'm sorry, that is -2. This is what's called the big circle relation. Delta is equal to -2. Delta is the loop that surrounds all end punctures of the sphere. Okay, so if you guys are wondering if there's like an explicit formula to compute delta and gamma ij positive and negative, we could do so as combinations of beta ij. So this is our lemma. This is our proposition right here. For any I that's a subset of interval ij, let I sub k be the kth element of I, set I sub o equal to I, and I sub cardinality of big I plus 1 equal to j. Then in the sphere, the end puncture sphere, this is the formula for gamma ij positive and negative. Let's talk about the idea of the proof. So is everyone following so far about how I explain gamma ij positive and negative? Yes.
Farhan, do you mind if I say something quickly and maybe clear up some things?
Yeah, sure.
Make things a little simpler.
Yeah.
So the I think a lot of these relations have a nice geometric interpretation, which Farhan emphasized, but I think it's just a lot easier to see. Is that many of these relations basically say the first one, the Ptolemy relations, says that if you have an intersection essentially like this from, let's say, this puncture to this, if you have like a rectangle or 4 different punctures, 4 subset, that if you have an intersection like this, you can resolve it into the sum of these 2 curves. And that for gamma relations, if you have a curve that goes around all the other punctures from between 2 punctures, you can essentially wrap it around the sphere. So, and the other one's a big circle relation, that if you have a circle that encloses all of punctures, you can just wrap it around and turn it into a sphere that contains none of the punctures. So that's one of the big reasons of why we're able to do this, is there's a nice geometric interpretations that lead into these algebraic equations. And also the VIs, and as I said before, those 2 curves gammas, the gamma ij's, those 2 can be broken down into VIs and beta ij's. That's what the generators proof also showed, is that we can always break them down. And that's the explicit formula. They're a little complicated. It's still a bunch of products and sums.
Okay, thank you, Ryan, for your comment. So let's talk about the proof for this formula right here. We are going to let k be an integer in between I and j. We will define eta ikj as the reduced R class starting at vi, moving in a clockwise direction below v sub k minus 1 and above v sub k, arriving at vj. So this is a figure I'm talking about. So eta ikj is an arc that starts off at vi. It's going to go above vk minus 1 and below v sub k, and it's going to continue going in above the other vertices in a clockwise direction until it reaches vj. If you were to draw eta I plus 1j, you're going to get the gamma ij positive. If you were to draw eta ij minus 1j, you should get beta ij. So we could apply the puncture scheme relation on v sub k, and by doing so, we will obtain this recursive formula right here. We could apply this formula to gamma ij positive and use induction. That's all I have to say. If you guys are interested, then I could talk about the other explicit formula for delta. But we could say that until after this presentation ends. Is everyone okay so far? Yeah, take that as a yes. Take it away, Matt.
All right, and yeah, I'm gonna finish the proof that we had in our paper. Let's just, here it is. All right, so once again, this was originally a separate presentation. So this was originally a separate presentation. So basically everything here is unnecessary to worry about, as it was already repeated in both of the other parts. What's important to what my part of the presentation speaks about is that the first relations that Farhan described, the Ptolemaic relation, actually defines the Skein algebra for the n-punctured plane. That's another part of our paper. If the actual goal of our paper was to define the classical Skein algebra of the punctured sphere, but we also found that there was a very nice presentation for the punctured plane, Skein algebra of the punctured plane. And that was simply the same generators, and only the ideal formed out of the Ptolemaic relations. That would be not including the gamma relations and not including the big circle relation. Once we got the classical Skein algebra of the punctured plane, we saw that there's a very natural homomorphism, a very natural function from the Skein algebra of the punctured plane to the Skein algebra of the punctured sphere. The simple homomorphism is we just map it. There's a really nice, take whatever map you want from the plane to the sphere, and that map is going to map punctures to punctures and multicurves to multicurves. So that homomorphism we called iota prime. We never actually said it out loud, but that's the homomorphism. So we also thought, hey, what is the kernel of the homomorphism? What things in the homomorphism map to 0? Map to no multicurve, just blank. And the answer to that was any element where you pass a strand over the point at infinity. That's the nature of all homomorphisms from the plane to the sphere. There's always going to be one point on the sphere that is not hit by the homomorphism. If there's a pretty natural map, I believe it's called the Poincaré map, that does not map the North Pole to anywhere, for instance. Generally, this is just kind of accepted. And in a multicurve, we can pick a little part of the multicurve out, which we call a strand, and we can pass it over that point at infinity. On the plane, on the punctured plane, these are going to be two separate multicurves. For example, one example of this is the gamma relations. We have the arc from 1 to 3, pass a little strand of it. Let's say right here, we pass it over the point at infinity, and we're going to get gamma 3, 1. And these are going to be two separate multicurves in the curve algebra of the punctured plane, but it's going to be the same multicurve in the real algebra of the punctured sphere. So the gamma 1, 3 minus gamma 3, 1 would be mapped to 0 under this homomorphism. So what we tried to do in this part of the paper and in my presentation is prove that this is the case. That if something is in the kernel, then it belongs to the ideal formed by the gamma and the big circle relations. And obviously the backward step is trivial. If something is generated by the gamma relations or the big circle relations, obviously it is in the kernel, sort of by definition. So yeah, this part is just defining what the gamma and big circle relations are, and the fact that all of the gamma and big circle relations fundamentally are passing strands over infinity. Here's just a redefinition, and now we get to my proof. The way we prove this is once we had some multicurve alpha, we passed a little strand of it over the point in infinity, getting alpha c. What we then tried to do is simplify alpha until it was so simple it could be described by the gamma and big circle relations. Our first step was to apply the Skein and relation and the puncture Skein relation to remove any crossings, any self-intersections. This is possible because both the crossing the strand over the point at infinity, and all the skein relations, they're all fully local. So we can apply them to one part of the multicurve and have it not affect any other part. What this implies is that when we separate alpha into the sum of Ci alpha I, that each of the alpha I is going to contain that little strand that we take over infinity. And if we assume that any reduced multicurve satisfies this sort of ideal property, then we've proven it for the multicurves containing crossings. So this would be the first step. We don't need to worry about crossings. We can only focus on multicurves without crossings. A second step that was not featured, that I didn't write onto this poster, was removing any loops and things like that. Loops fundamentally can be broken down into sums and products of beta ij's. So that was just that was sort of not a part of this proof, because we could only focus on sums and products of arcs. But moving aside from that, we can now reduce the complexity of any multicurve composed out of sums and products of arcs that do not intersect each other. Out of these arcs, let's say we've separated alpha into some sum and product of arcs that don't intersect each other. Only one of these arcs is going to contain that strand that crosses over P. So we can only focus on that one. Now this arc can be as complicated as it wants. It can wind around the points as many times as it wants, but we can define a complexity measure for it. This complexity measure would be C alpha. I'm not going to go over how C alpha is defined because it is a bit complicated. It counts not only how intertwined the arc is with the polygon P, but also how many points it separates from each other. What is the minimum number of points that it separates? It's generally complicated, so you might have to take it a bit on faith that the complexity deduction we do actually reduces the complexity. The full details of it are present in our paper, though. So, for example, this image has an example of a curve alpha with C alpha equal to 4, 2. It winds in and out of the polygon 4 times, and it separates 2 points right here. That's generally one way you can think of that. So what we're then going to do is we're going to do this complexity deduction, which is fundamentally just the puncture skein relation applied backwards. You can see if you bring this over to this side, if you bring this term over to this side and multiply both sides by VI inverse, you're just going to get the puncture skein relation on this vertex. What we then say is, by our definition, we've separated alpha into a sum and product of delta 1, delta 2, and epsilon, all curves of which have a lower complexity than alpha. And epsilon is going to contain the strand that crosses over infinity, and one of delta 1 and delta 2 will. Let's say delta 2. Once we have this, we've proven that if, by sort of strong induction type argument, if our proof works for any curve with a lower complexity than, let's say, our alpha, if it works for all those types of arcs, it will work for alpha as well. And this completes our induction. This proves it for any arc. It proves it for any product of arcs. It then proves it for any loops, and then it proves it for any product of loops and arcs that crosses each other by step 1. So this completes our induction and ultimately our proof that the curve algebra of the curve algebra of the real punctured sphere has this presentation, where J is composed out of the Ptolemaic and gamma and big circle relations. So yeah, that's it.
Yes, that was our presentation, and obviously I can answer any questions or anything. So please, if you have any questions or
please ask
any
questions if you
concerns,
have
please
any.
let us know.
I will. I'll just keep on sharing just in case anyone needs me to point to things, because for questions.
Just a I guess maybe like a meta question. What was the motivation for you guys for this project?
Who wants to
Matt,
answer this?
You want who? Do you want? Actually, I'll take this one. I'll let you guys take the rest. Of
Okay.
it. The motivation, the skein algebra actually, which I forgot to mention at the beginning, comes from it's a topic from knot theory. So essentially, one way to distinguish a knot is you can think of it as many ways. If you take simply a circle, I think that would actually, I'm not 100%, but I believe that's the simplest knot. If you were to take a embedding of multiple circles, that would be another knot. And many of these different ones are topologically different, meaning they can't be just easily deformed into the other ones. There's no ways to simply deform them. So one way of mathematicians, I think in like the 1900s, were trying to classify two different knots. So they created multiple different polynomials, which are called like the Jones polynomial. I think was one of them, the Homefly polynomial. And they all exhibited what we call the Skein relation, which is actually the first relation in this, the first relation on the bottom, the Skein relation. And from there, I mean, I think the Skein algebra was the polynomial that we're studying also has been, I think it's been used as a class. It was originally trying to make a better classification technique, but I think it ended up having some interesting applications to topics in hyperbolic geometry, topics in something called relating to something called the Teichmuller space, related to actually the case that we did is which is actually more general. This has to deal with the quantum Skein algebra, which I think is potentially also related to, has maybe some applications in like quantum mechanics or quantum physics. So there's like it's our professor who we worked with was very interested in the connections between many different fields. And if you found something for one field, it could lead to some more, more developments in others. So this sort of sat at the middle of like algebra topology, hyperbolic geometry sort of. There's a lot of things that are connected into this. So, and we were interested in doing some research, and he offered this project. It required basically a linear algebra background and then reading about algebra, a little bit of algebra, which wasn't too bad. But that was sort of the motivation of how this thing came about. And we just found basically an expression that describes explicitly what the Skein algebra is, because that hadn't been done in a previous paper. They didn't know like what curves could make up the Skein algebra, that set, what curves could create all the possible curves, and what were the extra relations that that exist for us to say that this is an isomorphism. So I hope that answers the question.
Yes, great, thank you.
Anyone else?
If anyone has questions related to the paper, related to any of us, related to research, any things. I know this is a theoretical research. I'm personally probably more interested in right now some form of mathematical finance or data science research, but this was definitely a very enjoyable experience. I did like working and learning about this stuff. I'm assuming no more questions.
Yeah, I guess you guys understood everything really well.
That was very, very good job. And no, I was happy to have you guys. And that's the end of our presentation. If you guys want to stick around, I can also give a little bit of information about the club if you have any questions. The club is actually more of an applied math thing, but our research we just wanted to present our research. We thought it would be an interesting thing for other students because we're trying to connect some undergraduates with grad student, master students. So thought maybe getting a perspective from an undergraduate would be interesting because we don't necessarily have, I have never taken an algebra class. I've never taken a topology class, but I can sort of get a little more of the intuition from an undergraduate perspective, which is a little naive, but still useful, I think, for if you're trying to do some form of undergraduate research or plan on going to a grad program. So I think I'm going to stop the recording, and then if anyone wants to ask any questions or stick around, or
we're gonna stick around here for some time.
If not, feel free to leave. And also, we can give you more information about how to get involved with the other events this semester. So please let us know.